Friends, now we are going to discuss the frequency response analysis of control system. So what is frequency response analysis? It is basically the steady state response of a system to the sinusoidal input. So clearly in the frequency response analysis, we learn the steady state response of a system to a sinusoidal input. Basically, whenever an input is given to a system, we get the response of a system, and it is composed of two parts. First is the transient response, and next is steady state response. The steady state response will occur when the transient response have died down. Like if I provide the input, if I provide a step input to a second order system, we will get an output like this. And you may see that after some period of time, the transient response have died down, and the body achieved its steady state value, and this steady state response is called as the frequency response analysis. So basically here what we do, we just vary the frequency of the input signal over a certain range and study the resulting response. There are different methods available for this. First is Nyquist plot, then Bode plot, and Nicholas chart analysis. The Nyquist plot is also called as polar plot. That is when we take the frequency from 0 to infinity, we call it polar plot, and when we take the frequency from minus infinity to infinity, the same plot will be called as Nyquist plot. So it's important to note that the polar plot will be from 0 to infinity, it is called as polar plot, and Nyquist plot, it is from minus infinity to infinity, it is called as Nyquist plot. So basically these are different methods to analysis the frequency response of a system. So first we will try to understand how we get the steady state output to sinusoidal inputs. So consider a system whose transfer function is given by Gs. Consider a system whose transfer function is given by Gs, and an input Xs is applied to it, and we get output equal to Ys. The correspondingly time domain input will be called as Xt, and time domain output will be called as Yt. So basically Xs is our input in Laplace domain, and Ys is in the output in Laplace domain. So if we put S is equal to j omega, we get the input and output in terms of frequency domain. So here the input we consider at equal to Xt, and Xt is equal to x sine omega t. So this is our first equation, that when the input is x sine omega t, it is a sinusoidal input, and if we apply this input to a stable linear time invariant system, that is LTI system. So what is the property of LTI system? LTI system, basically you may remember that if we apply two input independently to an LTI system, or the input is composed of two parts having value a1 x1 and a2 x2, if we apply the sum of these two input to the LTI system, we get output equal to a1 y1 plus a2 y2, where y1 is the output corresponding to input x1 for LTI system, and y2 is the output corresponding to x2. So if the input is the sum of two individual inputs, and then the output will be again the sum of outputs corresponding to their respective inputs. So basically this is the property of LTI system. Now what is meant by time invariant system? So time invariant system is that the time shift in input does not affect the property of output. That is, time shift in input does not affect the property of output. That is, if if the output will be yt corresponding to input xt, then if we shift the input by an amount time by an time t, that is, if we instead of input xt, if we apply the input xt minus capital T to the input gs, or it's for the LTI system, then we get output equal to yt minus t. That is, the change in the input or the time shift in the input will not affect the property of output. That is where yt is the output corresponding to input xt. So here also the time shift in input produces an equal shift in the output. So we have learned about this LTI system, and if the input x sine omega t will be applied to this system, we get an output equal to yt. Now this ys is the Laplace transformation of this output yt, and similarly xs is the Laplace transformation of input xt. Then output will be yt is equal to gt convolution xt. As we know that for an system, if its transfer function will be gs and input xt will be applied, then the output will be convolution of gt and xt. So what is basically convolution? Convolution is a mathematical operation that which take place between two functions and produces a third function that represents the amount of overlap between one function and reverse and translated version of other function. That is, it basically represents, see, if I write the equation for this, then it will be equal to minus infinity to infinity, yt is equal to minus infinity to infinity f tau into g t minus tau d tau. So if you see this equation, this basically represents your convolution. So it represents the amount of overlap between one function f tau and a reverse and translated version of other function, that is g t minus tau, and it produces a third function equal to yt. We may write it in other way also. It is yt is equal to minus infinity to infinity g tau f t minus tau d tau, where tau is a random variable. Okay, we are taking it as a variable. So if we apply the if we obtain output in terms of time domain, we will get as a convolution of gt and ft. However, when we take it into the frequency domain or in the Laplace domain, we get the output is equal to ys, and convolution will be changed to multiplication. That is, Laplace transformation of gt convolution ft or xt, which will be changed to gs into xs. It is a very well-known property that the convolution will be changed to a multiplication in Laplace domain. So ys is equal to gs into xs. So the output will be given by, so if from there, if I put the value of input xt, that is x omega t, we get the output of the system will be given by yt is equal to x into m into sine omega t plus phi. That is, the amplitude of output will be the product of amplitude of input into the magnitude of transfer function, and it is the phase of this output will be given by omega t plus phi, where phi is the angle phase angle of transfer function. So in this way we may write that yt is equal to xm sine omega t plus angle of gj omega, because phi is the angle of gj omega. So m is the, so it is written here also, m is the amplitude ratio of output and sinusoidal input function, and phi is the phase shift between input and output sinusoidal function. So basically what you should keep in mind, you should keep in mind that if the input is x sine omega t, that is if the input is a sinusoidal input and it is applied to a transfer function that is gj omega given by m into e to the power j phi, then the output will be xm sine omega t plus phi. Okay, so in the output angle phi will be introduced due to transfer function. This angle phi will be introduced due to transfer function, and the magnitude of this transfer function will be multiplied by the magnitude of input or the amplitude of input. So this is the concept. Now you may see that I have drawn this figure that when the input is xt, x sine omega t, it is represented by this curve. Okay, and the output is equal to yt is equal to y sine omega t plus phi, that is YSST. In fact it's a steady state, so YSST is equal to y sine omega t plus phi, where y is equal to x into m. M is the magnitude of transfer function and x is the amplitude of input. So you may see that y may be more than x or less than x depending on the value of m, first thing. And second thing is that the phase angle will be changed by, the phase angle of output will be changed by the introduction of a phase angle due to transfer function, and the output will be y sine omega t plus phi. So whether if the phi will be positive or the negative, then the output will be shifted from the input. So for LTI system, the output has the same input, same frequency as input at the steady state. So it's also an important point that if you see that the output has the same frequency as input at the steady state, their input also frequency was omega and output the frequency is omega. Amplitude of output is given by product of that of input and mod gj omega. So it is also clear from this that y is equal to x into m, and the phase angle of output differ from the input by an amount phi equal to angle gj omega. It is also clear from the expression of this steady state response of the output. So here comes the concept of phase angle, phase lag or phase lead network. What is meant by phase lag network and phase lead network? So if we get the positive phase angle, as we have already learned that the output YSST is equal to y sine omega t plus phi. So if phi is positive, then the transfer function is producing a positive phase in the input, and we may say that it is having positive phase lead network, or it will have phase lead characteristic. So the system will be called as phase lead network. Similarly, if the transfer function phi will be negative, then it's a negative phase angle, and the system having a phase lag characteristic, and it is called as phase lag network. So we have learned that how we determine that whether any system is phase lead network or phase lag network based on the phase angle phi. Now we will make a quick recap of concepts and formula we have learned. So as we know that the steady state response of a system to a sinusoidal input is the basically it is the frequency response analysis of the system. So if we study the frequency response analysis of a system, then it is a steady state response analysis of the system. And if an input is applied to the system, it will have the output have two components, that one is the transient response and another is the steady state response. After some period of time, the transient response died and we get the steady state response. So there are various methods available to analyze the steady state response of a system, in which we vary the frequency of the input and we see the corresponding output. So these are the various methods: Bode plot, Nyquist plot, Nicholas chart and analysis. So now we also have learned that how we get the steady state output to sinusoidal input. So if the input is x sine omega t and it is subjected to an LTI system having transfer function gs, then we have learned that the output will be given by yt is equal to x into m. It's a multiplication, not convolution. So output is in fact it's a steady state output. That is, steady state output is equal to amplitude magnitude of the transfer function into amplitude of input is the, so this product will be the amplitude of output, and the second part is the sine omega t plus phi, where phi is the angle, phi is the phase shift due to transfer function. That is, if the transfer function is gj omega, and if it is written in the form of m e to the power j phi, then m is the magnitude of this transfer function and phi is the phase angle. So this phase angle produces the phase shift in the output. So yt is written as x into m sine omega t plus phi, where phi is equal to angle of gj omega and it is equal to y sine omega t plus phi. So we have learned that for an LTI system, the output has same frequency as input at the steady state. First thing. Second thing is that the amplitude of output is given by the product of that of input and the mod of gj omega, where mod of gj omega is equal to m, and we have seen that the amplitude of output is x into m. So it is written here, and the phase angle of output differs from input by an amount phase shift produced by this transfer function, that is phi is equal to angle of gj omega. So based on this phase shift, we will have concept of phase lag and phase lead network. So if the value of phi is positive, then it will have phase lead characteristic, and the corresponding network is called as phase lead network. Similarly, for negative phase angle, it will have a phase lag characteristic, and the corresponding network is called as phase lag network. So in this way, we can obtain the steady state output to a sinusoidal input, and correspondingly we can calculate that whether the transfer function is given by an equation is a phase lead or phase lag network.